This paper introduces Polarized 3D, a technique to enhance 3D photography by leveraging polarization cues. A core step map from a commodity depth sensor is used as input along with an off-the-shelf camera equipped with a polarizer. 3 photos are captured at 3 polarizer angles. The input depth map is coarse and lacks detail. Our algorithm uses optical information in the polarized photos to obtain a reconstruction at right. Notice that the fine geometric detail has been recovered accurately. Please see the project page for details.
In air, the radiance arriving in an object is given by the direct source radiance. In a medium, there is also forward scatter from the source. Similarly, the radiance arriving at a camera in air is given by the direct object radiance. In a medium, there is also forward scatter from the object as well as backscatter from the source. Our algorithm takes as input 3 or more images under varying illumination. First, we remove the backscatter. Next, we deblur the object forward scatter. Then we approximate the source forward scatter to give a simple system of linear equations, which we solve for the surface normals, and then we integrate to recover the surface. Here are our results for a medium of low turbidity. On the left, we can see that just accounting for the backscatter either by subtraction top or fluorescence bottom is not enough. On the right, we see that after also deblurring, a faithful reconstruction of the surface is produced. In high turbidity, again just handling the backscatter is not enough. However, deblurring backscatter subtracted images fails due to low signal-to-noise ratio, while deblurring fluorescence succeeds.
We can find all kinds of transparent objects everywhere in our daily life, in the office or at home. Can we segment the transparent objects automatically from an image? Our proposed method, transcart, can segment transparent objects from a light-filled image. Light rays from background are linearly distributed. However, light rays from transparent objects are not linearly distributed. We call this LF linearity. We also design a occlusion detector to get the boundary. LF linearity and occlusion boundary are incorporated with GraphCart and get good results.
We first show example scene flow results and a virtual reality application for a moving hand holding a piece of paper. Our inputs are consecutive frames captured with a Litro Elim light-field camera at different points in time, and we can see visualizations of the optical flow and the flow in depth. Now, we place a virtual highlight over some text on the paper and propagate this edit through the video by moving the highlight in 3D space using the calculated scene flow results. Note how the highlight correctly follows the movement of the text and correctly appears smaller as the text moves away from the camera. Next, we show an application for follow focus, with an example scene of a tennis ball that moves. We select a point on the ball in the first frame, and by calculating the scene flow between consecutive frames, we are able to automatically refocus the light field image for each frame to keep the initial point on the ball in focus.
It is a long-standing hypothesis that intrinsic images should be estimated together, synergistically exploiting consistency between them. Here, we test the specific hypothesis that the extraction of shading and albedo improves the estimation of depth. We build upon a recent example-based depth estimation method called depth transfer. Here we show that working with albedo and shading instead of RGB values, we significantly improve depth estimation. This indoor scene is captured by a moving camera. We extract intrinsic images and use them synergistically for depth estimation. The baseline depth transfer method, on the left, estimates over-smooth and inaccurate depth. Our method, in the middle, estimates dense depth values preserving strong surface boundaries, similar to the ground truth. The fully metric method performs overall well, but the area at the bottom center shows large depth errors. We see our intrinsic depth method as a modest step towards a more integrated estimation of intrinsic images.
The underlying technology of phase-based time-of-flight cameras is a phase-encoded infrared signal. We propose to perform model-based object tracking directly on these raw infrared captures, thus utilizing the much higher frame rate of the infrared captures. Because we use the phase-encoded signal for tracking, our method allows to accurately infer the object's distance to the camera, even when the usual depth reconstruction fails due to fast motion of the object.
We present a time-of-flight-based depth-selective camera to image light coming only from the depth of interest. We demonstrate two applications, imaging through scattering media and virtual blue screening, by designing depth sensitivity that suits each application. A time-of-flight camera measures cross-correlation between a temporally modulated light source and a reference signal. We use M sequences, which have a triangle-shaped cross-correlation, as a basis to design the desired cross-correlation of the system. The main idea is to design arbitrary cross-correlation by superimposing shifted and scaled triangle functions. In this experiment, we suppress the backscattering of light from a scattering media. We place a few nets right in front of the camera to act as a scatterer. Our camera suppresses this back illumination and improves the contrast dramatically. We also demonstrate a virtual blue screen technique targeted at teleconferencing and cinematography. We programmatically modify the depth sensitivity to reject the photons coming from the background.
Throw a party.
I was just thinking the same thing. I mean, who puts out a single cheese plate for 20 people?
Right? What are you doing?
I'm gonna change these sheets.
Why?
Because it's disgusting. I mean,
You can't just make up your own rules to suit you as we play the game.
well, stop taking the fun out of it then.
I'm not taking the fun out of it. What takes the fun out of it is when you...
We got fuzzy as
from emotions to action units with hidden and semi-hidden task learning. Limited training data in action unit recognition can decrease the performance of learned models. In this work, we ask if it's possible to use additional images annotated according to the 6 prototypical facial expressions in order to learn better action unit classifiers. For this purpose, we propose hidden task and semi-hidden task learning frameworks. These frameworks can be used in problems where we want to learn a set of hidden tasks, for which training data is limited, action units, but training samples are easier to obtain from a set of related visible tasks, facial expressions. To do so, these frameworks exploit prior knowledge about the relation between hidden and visible tasks. Comparing the proposed approaches with traditional single task learning, we show that the use of additional facial expression data can increase the performance of action unit classifiers. You can find more details in the original paper.
Smarter looking people are not that smarter, but we may think they are because the face can make a strong impression about the person. In this paper, we want to train a model that can automatically infer the perceived traits such as competence or intelligence from facial photographs. And then we use these traits to predict the outcomes of real-world social events such as political elections. We propose a hierarchical model incorporating a lot of image features as well as mid-level facial attributes. On top of that, we have a layer of ranking functions which train high-level social dimensions of a face. In our new dataset, we have 14 distinct social dimensions annotated on the pairs of images, such as intelligence and attractiveness. Our results indicate both the election outcomes and party affiliation can be classified just using faces. Details can be found in the paper. Thank you.
We address face attributes prediction in this work. A large-scale face attributes dataset has been proposed. We perform face localization and attribute prediction jointly using only image-level attribute tags. The overall pipeline consists of 2 face localization nets and 1 attribute prediction net. Rich attribute information can facilitate face localization. Pre-training with identities discovers attributes such as race. Subsequent fine-tuning expands attributes such as thick lip. Our approach achieves state-of-the-art performance both in face localization and attribute prediction. Thanks.
In real-world person re-identification, images of people captured at very different resolutions from different locations need be matched. We call this the low-resolution person re-identification. To solve this new problem, we propose a novel joint multiscale learning framework, termed Joint Multiscale Discriminant Component Analysis. The key component of this framework is a heterogeneous class mean discrepancy criterion for cross-scale image domain alignment, which is optimized simultaneously with discriminant modeling across multiple scales in the joint learning framework. Our experiments show that the proposed framework outperforms existing representative re-identification methods as well as other related low-resolution visual matching models applied for the low-resolution person re-ID problem.
Eye images captured under relaxed constraints usually accompany more noise and occlusion, therefore leading to a high failure rate for iris segmentation using traditional approaches. In this paper, we proposed the RTVL1 energy regularizer, which can suppress the noise effectively and thus help localizing the iris circle accurately. Based on the iris position localized, we developed a series of robust post-processing operation which fine-tunes the boundary of the iris mask to improve the accuracy. Then we can obtain the automatically segmented iris region. The experimental results show that the proposed approach has achieved the lowest segmentation error, compared with several state-of-the-art methods. Besides, the iris recognition performance has also been improved, using the iris masks generated from the proposed approach.
Okay, our paper, Regressive Trace Structure Model for Facial Landmark Localization, presented by Jishen Xu. Trace Structure Model proposed by Zhu and Remnant in CVPR 2012 is good. However, it's too slow at runtime. That's why we propose the Regressive Trace Structure Model. It has three components. The first is the coarse version of Trace Structure Model. It's good for coarse, however, fast fixation. And the second component is the refined trace structure model, and it's good for removing the false objects. And the third component is the regressive estimation. It's good for localized dense set of visual landmarks. And the performance, as you can see in this table, it can be 10 times or up to 70 times faster than the original versions of trace structure model. And thank you for watching.
to predict salinity on face images. Motivations for salinity detection in face images. When the face becomes larger, face and facial features draw more fixations. Based on the motivations, it takes 4 steps for our model. Step 1. We establish the eye tracking database of face images. Step 2. We found that the statistical analysis is corresponding to our motivations. Step 3. For salinity detection, both bottom-up and top-down features are taken into account. In our method, a new channel on facial features is added. Then, both top-down channels are learned with GMM. Also, the weights are learned by least square fitting. Step 4. The results shows that our method advances other methods. Thanks.
But somehow we've managed to attract some more amazing people.
With meeting me and understanding that I was going to be representing him somewhere, he probably wanted some other actor to play himself.
Not only have we got Ben and Naomi back, and obviously Rafe and
our capacity to assimilate people. It's a very difficult bill to pass because there's a lot of moving parts, and the legislative process can be ugly. and
He told me that Mary is leaving for California at the end of the month. He told me that Mary is leaving for California at the end of the month. I met Frank last night in a bar. He told me that Mary is leaving for California at the end of the month. She will stay there for a whole year. A whole year.
In this work, we try to understand what does an image tell us about the temperature. In his grain stack paintings, Claude Monet shows us the exact same scene, but manages to convey the essence of two different seasons. When I wake up in the morning, I have to decide what I'm going to wear. I usually go to the window and peek outside. A glance suffices to tell me if I'll need a jacket today. To explore interactions between images and temperature, we collected a dataset of temperature-annotated outdoor scenes. The dataset includes rural and urban scenes and covers a variety of environments and climates from different locations in the United States. In the paper, we explore correlations between image sequences and the temperature. We apply supervised learning to use a webcam as a crude temperature sensor. We even synthesize the appearance of a scene at a given temperature. Interested to learn more? Please visit our poster or check out the paper. Thank you.